Unit 5.6 Fundamental Theorem of Algebra. In this class, we're going to learn how to use the fundamental theorem of algebra to solve polynomial equations with complex solutions. Let me give you an overview. The fundamental theorem of algebra will tell you how many solutions you are going to have when you solve a polynomial equation. The solutions might be real or imaginary, or sometimes we call it complex solutions. Let's start our discussion with the simplest form of polynomials of degree 2. Once we see a polynomial with degree 2, we know this is a quadratic and the graph got to be a parabola like this or like this. And when you put this parabola into an xy coordinate plane, there are only three scenarios. The first scenario is that the parabola crosses the x-axis through these 2 points. And these 2 points are the zeros, or the x-intercept, or the roots, or the solutions of these quadratic equations. If we solve it algebraically, we're going to have y equal to x squared minus 2 squared. 2 squared means 4. The reason I change it like this because I want to make use of the difference of square. And then we have y equal to x plus 2 times x minus 2. We set it to equal to 0, so we can make use of the zero product property, and then we finally getting x equal to negative 2 or x equal to 2, which is right here and there. And these are the roots for these quadratic equations. Because they are on the real number line, that's why we call it two real zeros. Now let's take a look at the second scenario. The parabola didn't really cross the x-axis, it only touches the x-axis one time. And it looks like we have only one real zero. But if you try to solve it algebraically, we are going to have y equal to, again, we set it to equal to 0 later, but right now let's rewrite that like this. And then we set it to 0, and then we have x minus 1 times x minus 1. And we have x equal to 1 or x equal to 1. Technically, we still have two real zeros. And in this particular case, we call it is a root of multiplicity 2 at 1. From the graph, yes, we have only one real zero. Technically, we have two real solutions. The last scenario of the parabola will be like this. In this case, the parabola didn't even touch or cross the x-axis. Since it didn't cross the x-axis, we say there's no real zeros. Or we can say there's no real roots. But if you use quadratic formula or completing the square to solve this, you have actually two complex roots, which is x equal to negative 1 plus I, or x equal to negative 1 negative I. In other words, even though we don't have the real roots, or real zero, we do have two complex roots, which are right here already. Now let me summarize what we have learned so far. In a polynomial of degree 2, we have three scenarios: 1, 2, 3. And in the scenario 1, we have two real roots. And in the scenario 2, even though we said we have one real root, but it's actually is a root of multiplicity 2 and 1. So technically, we still have two real roots. It just happened they're the same value. The last scenario, from the graph, we know there's no real roots. But if we solve it by quadratic formula, we know we're gonna end up having two imaginary or complex roots. If you look at the whole thing, all these parabolas have two roots. It could be imaginary, it could be real, it could be a multiplicity. But we know these three has two roots. And that's what the fundamental theorem of algebra telling us. We just have to look at the degree of the polynomial function. Say if it's n, in this case equal to 2, then we know the number of solutions of this polynomial is going to be equal to 2 as well. In other words, if the degree of the polynomial function is 3, we're going to have 3 solutions. If it's 4, then we have 4 solutions. That's what we call fundamental theorem of algebra. Here is the formal definition of the fundamental theorem of algebra. So if a polynomial function has a degree of n bigger than 1 or equal to 1, then px equal to 0 has exactly n roots, which include multiplicity and the imaginary roots. So if I give you an example, you have say x cubed plus 3x squared plus 4x equal to 0, then you know they have 3 roots. It could be imaginary, it could be real, it could be complex, it could be a combination of these two. If you have x, say 3x to the 4th power plus 3 x squared plus 4x minus 2 equal to 0, because the biggest degree of this polynomial function is 4, so you know it's going to be having 4 roots. Like I said, one more time, it could be real roots, multiplicity, or imaginary roots. In this PowerPoint slide, I'm going to show you how to make use of fundamental theorem of algebra to find all the roots of a polynomial function. And in this case, first we have to identify the biggest number of the degrees in the function. And in this case, we know it's 5. Once we have 5, which is the biggest number or biggest degree of the function, we know there will be 5 roots. Again, it could be imaginary or it could be real. The roots are actually the zeros of the function. So we have to combine all the skills that we learned before, such as rational root theorem, the factor theorem, syntactic division, and factoring, all these techniques that we learned to find all the zeros or the roots of this polynomial function. But we know for sure there would be 5 roots. Now let me walk you through the whole process step by step. First, we have to make use of the rational root theorem to identify the possible rational roots of this polynomial equation. The possible rational roots according to the rational root theorem is the factor of the constant term over the factor of the leading coefficient. So in this case, factor of the constant term, which is 4, is plus n minus 1 plus minus 2 and plus minus 4. And the factor of the leading coefficient means the coefficient of the variable which has the biggest power. In this case, the leading term here is x to the 5th power, and the coefficient of this leading term is 1. So all these actually over 1. Since it's over 1, that means the rational roots gonna be plus and minus 1 or plus minus 2 and plus and minus 4. Once the possible rational roots were identified, and in this case you get plus and minus 1, plus and minus 2 and plus and minus 4. The next step, we have to evaluate every single possible roots here to see if they are really the factor or the roots of this equation. So the evaluation process is actually plug in 1 back to this whole equation, and if it's equal to 0, then we know 1 is a root. And if 1 is the root, then x minus 1 is the linear factor of this polynomial expression. Once we find the first linear factor, x minus 1, we can use synthetic division to factor the whole polynomial expression out. After you do the synthetic division, you find out the product of two factors of this polynomial expression. They are x minus 1, which is the first factor, and then we have x to the 4th power, which is this one, minus 3x squared minus 4. Then we keep factoring out by using the sum of the factors strategy. Then we have another two factors right here. Since they are not linear yet, we have to keep factoring until they become linear factor. That means they are to the power of 1. For this one, x squared minus 4, we can make use of the difference of square and end up, well, let me show you one more step then. X squared minus 4 basically means x squared minus 2 squared. So this is the difference of square. That's why you have x minus 2 times x plus 2. For this one, we use the sum of square, which you end up getting this. After you get all this, you set everything equal to 0, then you can find all the roots. So set all this up equal to 0 and solve for x. Set everything equal to 0 because of the zero product property. Then you can find all the roots right here. By the fundamental theorem of algebra, you know there are 5 roots. 1, 2, 3, 4, and 5. As you can see, 1, 2, and negative 2 are the real roots. And I and negative I is the imaginary roots. But altogether, there are 5. Just like what we start the whole PowerPoint slide, we said because the greatest power of the leading term is 5. According to the fundamental theorem of algebra, we know there are 5 solutions. And we have 3 real solutions and 2 imaginary solutions.